I'm going to talk about the decadal simulations of ocean currents, temperature, and the salinity in the eastern Arctic Ocean. This talk will focus on Fram Strait because it is one of the major pathways for Atlantic water into the central Arctic Ocean. Atlantic water is a major heat source for the central Arctic Ocean. It moves into the central Arctic Ocean through Fram Strait, moves cyclonically along the edge of the central Arctic Basin, and maintains a warm Atlantic water layer. If we look at the vertical profile of ocean temperature across this line, we can see it is a three-layer system. The surface water is near the freezing point because it is covered with sea ice. The bottom water is Arctic water, is also very cold. Between 200 meter and 900 meter, it is Atlantic water layer. It is relatively warm and salty. For atmospheric surface forcing, on climate scale, we can see there is a low pressure system in North Atlantic called Icelandic low. If we look at the storm track, we can see there is a storm track extending from North Atlantic to Greenland Sea. So the Greenland Sea is dominated by Arctic storms. In this study, we try to understand the impacts of Arctic storms on the Atlantic water inflow through Fram Strait. To understand the decadal variations of Atlantic water inflow through Fram Strait, we set up a nice ocean model based on NEMO 3.6. Its ocean component is OPA and ice component is NEM2. It has a quarter-degree horizontal resolution and 50 vertical levels. We also apply Neptune skin to better represent the Atlantic water circulation in the central Arctic Ocean. The river runoff is prescribed using a climatology. Lateral boundary conditions are pH-C, ocean temperature and salinity, and glorious ocean currents. Atmospheric surface forcing is JRA 55. We ran the model from 1958 to 2021. First, we have to validate our model results. Here we have the currents across Fram Strait along this red line. It is 78.8 degrees north. On the eastern side of Fram Strait, it is a Spitsbergen current. In the middle of Fram Strait, it is Arctic outflow. Our model can reproduce the spatial pattern, but its currents are a little bit weaker compared to glorious data. The spatial pattern of ocean temperature is consistent with the currents. On the eastern side of the Fram Strait is Atlantic water, which is relatively warm. On the western side is cold Arctic water. Our model can reproduce the spatial pattern, but a little bit of estimates the Atlantic water temperature. It's a similar story for ocean salinity. On the eastern side of Fram Strait is salt Atlantic water. On the western side is fresh Arctic water. Our model simulation has a very similar pattern, but a little bit underestimates the ocean salinity across Fram Strait. Next up, we are talking about Atlantic water inflow through Fram Strait. Here we have Atlantic water volume transport through Fram Strait along this red line. It is computed for the water with a temperature above 2 degrees Celsius. The black line is observations published in 2012. The red line is model simulations. We can see the model can reproduce the interannual and annual variations pretty well. Both model simulation and observations show a strong transport in winter, but a weak transport in summer. On the interannual scale, we can see a strong transport in the early 2000s, a weak transport in the late 2000s. The average transport from 1998 to 2012 is 2.03 Svidrov for model simulation and 1.98 Svidrov for observations, so they are very close. Now I will talk about the winter Atlantic water volume transport. The red line is model simulations and the black line is observations. The transport increases from 1960 to the early 1990s, but it decreases afterwards, and showing a significant decadal variation. The observations also show a decrease from 1998 to 2012 that is consistent with model simulations. I should mention that there are two warming events, one in the early 90s, the other one in the middle of 2000s. We do see two peaks, but they are just part of interannual variations. There is no significant trend. Next, we will try to understand the impacts of Arctic storms on the Atlantic water inflow. Here we have wind storm track density. In the 1960s and the 2000s, when the Atlantic water inflow is weak, the storm track extends from North Atlantic into the Barents Sea. It is almost a straight line. But in the 1980s, when the Atlantic water inflow is strong, the storm track shifts northward. There is a significant increase in the storminess near Greenland Sea. So we select a box in the Greenland Sea to compute the average storm track density. The black line is the average storm track density, and the red line is Atlantic water volume transport. We can see when there are more storms near Fram Strait, the transport tends to be stronger. When there are less storms near Fram Strait, the transport tends to be weaker. There is a significant correlation between Atlantic water volume transport and the average storm track density. The correlation coefficient is 0.41. It's quite significant. Arctic storm affects Atlantic water inflow through atmospheric surface forcing. Here we show the 10-meter wind anomalies relative to a long-term average. In the 1960s and the 2000s, when there are fewer Arctic storms in the Greenland Sea, we can see an anticyclonic circulation anomaly. West Spitsbergen is dominated by a northerly wind anomaly, which can weaken the Atlantic water inflow. On the other hand, when there are more Arctic storms, we can see a cyclonic circulation. West Spitsbergen is dominated by south wind anomaly, so the Atlantic water inflow tends to be strong. Next, I will talk about the heat flux of Atlantic water inflow. This is ocean temperature average along this red line. There is an increasing trend from 1960 to 2021, so the Atlantic water inflow is becoming warming in recent decades. It's a similar story for heat flux. There is an increasing trend from 1960 to 2021. Consistent with observations, there are two warming events, one in the early 1990s, the other one in the middle of 2000s. Based on our model results, the two warming events are related to the interannual variation of water volume transport and the warming trend in ocean temperature. The Arctic warming can also impact the salinity. This is the average salinity along the red line. There is an increasing trend from 1960 to 2021, so the Atlantic water inflow is becoming shorter in recent decades. That could be related to decreased ice export through Fram Strait and increased surface evaporation. Finally, I will give a short summary. There is a significant decadal variation of Atlantic water inflow through Fram Strait. When there are more storms over eastern Greenland Sea, West Spitsbergen is dominated by southerly wind anomalies which can enhance Atlantic water inflow. There is an increasing trend in the heat flux associated with the Atlantic water inflow due to the warming in recent decades. the salinity of the Atlantic water inflow tends to increase.
So Zhenxia is online, welcoming questions.
So I got in first, Paul. Yeah, so hi, Zhenxia, it's Greg Smith here. So I had a question here. I'll stand on the podium so you can see me. Yeah, so my question was just, I believe you said at the beginning your model was at a 1/4 degree resolution, whereas the Glory's boundary was 1/12, I believe. So I was just wondering if you'd compared those two at all already to get a feel for the impact of the resolution, and whether you thought that better resolving some of the eddy features could have an impact on the fluxes you're seeing, transports.
Yeah, I just the Glory's boundary is also 1/4 degree resolution. So I would say that's a great question. So we can see the model results and our observations. There's still a significant difference. So if we include this, I think the bias probably could be related to the low resolution, which cannot resolve the 80. So.
Okay, thank you. And I think Paul Myers here has a question for you as well. Go ahead, Paul.
Thanks for the talk, Zhenxia. Nice presentation. My question was, you were showing the changes in the transport of the inflow of the Atlantic water, the heat at Fram Strait with the change in the storm track. Do you then also see an out-of-phase behavior with the transport of the Atlantic water going in through the Barents Sea, aka when the storm track favors one route or the other? Do you get shifts between the relative importance of those two entry pathways?
No, that's a good question, but I didn't look at it, so that's probably